So the key here is the equations are great if you can figure them out. The real key is this relationship right here, recognizing a couple of things. One is that by convention, we start position at the maximum positive amplitude, but you could start it anywhere. But if you do that, then your position graph will be a cosine graph, velocity will be a negative sine graph, acceleration will be a negative cosine graph. And the connections work even if you start shifting, right? So if we were to shift the position graph by any amount, we just shift these other graphs by the exact same amount. They're still connected the same way. They are effectively 90 degrees out of phase, which seems weird because this object right here is not moving in a circle, but we can think about it as having one-dimensional motion that matches up with one of the dimensions of circular motion, one of the dimensions of rotation. One thing that I want to mention that we're not going to go into a lot of detail about because we don't have time, but if we think about energy, you have all the tools you need to think about energy for the systems that we've looked at. For horizontal spring mass systems, there is either elastic potential energy or kinetic energy or both. There's either energy stored in the spring or all of the energy is in the moving object or it's combined. And you can pretty easily look at how that would play out in terms of graphs of the energy, and what you would find is that it's going to be sinusoidal. For a pendulum, we either have gravitational potential energy, kinetic energy, or some combination of both. So if we look at a pendulum, it's all gravitational here, it's all kinetic at the bottom, and it's a mix in between. And if we assume conservation of energy, which isn't true but is largely true over short periods of time, we can think about how the total energy should always be the same. That means the sum of potential and kinetic energy should always be the same. That's going to lead us to some pretty inevitable and interesting conclusions about how those energies are going to relate to each other mathematically. I'm not going to go into that. You might choose to. And then what I want to have you all do starting today is think about what you're going to do for the last several days of class. And what I would like is for you to investigate something that is at least mildly interesting to you. I wanted to just throw out some ideas of things you could do, and then I'm going to give you the parameters of the project. So here's one thing you could think about. You could just take our spring mass system, this basic object oscillating vertically when hung from a spring, but when we looked at it, we used rulers and stopwatches. What if you used a motion detector? If you used a motion detector, then not only could you think about the initial values, the extreme values, and the equilibrium position and stuff, but you could get actual speeds and accelerations and positions at any time, which means you could build equations. You could actually look at the specific equations that define the motion, not just theoretical ones, but the actual ones. And if you wanted to look at energy, this would be a great way to do it. Because if you know the velocity at any time, you could easily find kinetic energy at any time. And since the total amount of kinetic and potential energy always has to be the same, you can look at the maximum kinetic energy, recognize that that's also going to be the sum of kinetic and potential energy, and you can use that to think about how much potential energy there is. And then with a spring on a mass oriented vertically, we have an extra interesting thing to think about, which is that there's all three types of energy here. There's kinetic energy, there's elastic potential energy, and there's gravitational potential energy. So you could then try to tease out where gravitational potential energy peaks, where elastic potential energy peaks, and how all three of those energies cycle together to create a constant overall energy. So that's one thing you could think about. Another thought is, what if you made your system itself more complex? So what if instead of making measurements a little bit more interesting and thinking about energy, what if you took two springs and you hooked them to the same mass, and you could make this oscillate vertically or horizontally. The way this is drawn, it's a horizontal oscillation, but you could do it however you want. What now? Like you figured out the period of a spring mass system for one mass. What about two? If we have two masses with the same spring constant, like what's the oscillation going to look like? What if you have springs with different spring constants? What if we have one with a large and one with a small spring constant? Like, what is going to happen? How's that going to play out? Yeah, let's just think about it, because I think this is something you can investigate. And I don't know. I mean, we could look it up. We could almost certainly figure it out by looking it up, but it'd be kind of fun to just experiment with it too. And another thing that I thought would be interesting to do would be to look at combination systems. So systems where we have like both a spring and a pendulum going. And in those systems, you could think about like, well, what kinds of what kinds of oscillations can you get where they sort of match up, and what happens if you, for example, were to put those together? Like, so you get this kind of motion, right? Like, this is kind of interesting motion to think about. It looks really complex, but it's really just two oscillations put together. What would the characteristics of the pendulum and of the spring need to be in order to make like a figure-8 pattern, sort of a horizontal figure-8 pattern? If you could figure out what those characteristics would need to be, then you could make pendulum with those characteristics and see, you test your prediction. Yeah?
For the previous slide, is there a way you could set up a system where one of the bottom spring is just strong enough that it just remains in motion forever?
No, that's a great question. No matter what you do, we cannot create a perpetual motion machine. But what we could do is we can extend the amount of time that a system goes by storing energy in different forms. So this, for example, is a pendulum clock. And pendulum clocks are super easy to make, super easy, because we know that the period of one full cycle is dependent only on the length of the string. So you get the right length and you have a clock. It's that simple. The problem is, if you hang something from a string like this, and the period is 1 second, and it only cycles like 15 or 20 times, then you've got a clock that only works for about 15 or 20 seconds. And you could either spend all of your life constantly resetting it, or you could just only keep track of time for 20 seconds, for 20-second intervals. So that's not great. But we have been using pendulum clocks for hundreds of years. So what's the deal? How do they do that? Well, it turns out that, you've all seen me doing this with the pendulum, right? It doesn't run out. What am I doing?
You're adding energy to it.
I'm adding a little tiny bit of energy to it. We can't make a perpetual motion machine, but we can add little tiny bits of energy. Now, it's not super helpful when it's a person adding those little tiny bits of energy. I can keep this pendulum going for a long time, but it's not very convenient. But what if we set up a machine to do it? And it turns out that's exactly how these pendulums work. And there's a few different ways that we can do it. One is we can plug them in, run them off electrical power, and then what happens is there is some sort of electrical component that gives the pendulum a tiny little push at the extremes of motion, so that it never dampens. That amplitude stays the same the whole time. Prior to the ability to use electricity, we could use springs, and that's interesting because we need to give the same amount of kick, right? That doesn't work too well if we have a spring that increases with force when it's stretched. If you wind up a clock to stretch a spring, there's more force here, less force here, it's not gonna match up. But we figured out how to make springs that exert a constant force. If we build the spring differently, then it's a constant force instead of a linear force with compression. Or May was telling us in that, I don't know about this, but she knows about clocks. In the other class was talking about how, well, the other thing that we can do is use basically a gravity battery. So what we do is we put something up here that gradually falls. And it's falling as that gravitational potential energy is used, is just used to kick the pendulum just a tiny little bit. So we've got like a gravity battery. There's a whole bunch of ways that we can do this. That would be a neat thing to look into. Like, what do you have to do to get this system to work? You know, you can't create perpetual motion, but we can store a bunch of energy and then use that energy to keep our system oscillating. Yeah.
Also, it's a bit of a side note, but I really like mechanical systems like that.
Yeah. Yeah, and so this is something like, it is highly unlikely that we will ever move entirely away from mechanical systems. Motion is almost certainly always going to be a thing. It's possible that at some point in the future, humans are going to be sitting in their pods with their, like, something plugged into their brain, and there's nothing moving, and that's it, and it's all just like, I don't know what. But I don't think so. I think we're always going to have motion. We're always going to have vehicles. We're always going to have motors. We're always going to have something where there is motion involved. Yeah?
Even at that point, there's still motion, there's chemical processes that include motion.
You would think, right? Yeah, I mean, it's little, like I hesitate to say never, because, like, if you would have said 50 years ago that we wouldn't be storing information on, like, magnetic tape, people would have thought you were crazy. And then if you would have said 20 years ago that we would have been able to store information without moving parts, there's like CDs and old hard drives, those all have like spinning, moving parts. But now we have solid state electronics. Your phone can store information without any mechanical motion at all. So maybe at some point we're going to be able to figure that out for like feeding tubes and like plugging ourselves into the matrix. But I don't think so. I think we're going to have motion for the foreseeable future. One thing you could look at is dampened oscillations. So this is where you have two sets of oscillations going, and they combine in such a way that the apparent motion is very slight, or it's extended over a long period of time. And this is how shock absorbers work. So this is like spring shocks, right? Like, you got a shock absorber, you've got a spring, and somehow this makes the ride feel less bumpy. And that's kind of brilliant. You could look at oscillations of musical notes, and that could involve something physical like a string vibrating, or it could be a column of air in a wood or a brass instrument or something. And then you could look at dampened oscillations like the spring shock absorbers, or you could look at amplified oscillations. And so this is like the drinking bird, which we're not going to watch this whole thing, but the way the drinking bird works is it, like, as you start it, it wobbles back and forth, and then it wobbles more and more and more and more, and as it wobbles, like, something is changing here, and then it just keeps wobbling and keeps wobbling, and then eventually it takes a sip of refreshing cool water, and then it starts wobbling again. And that's it. And somehow that there's like this cycle where there's like the big oscillation of getting a drink, and then there's these like wobbles that increase and increase and increase. And this isn't perpetual motion either. There's a whole bunch of thermodynamics that goes on behind this, but it's all really interesting. And so you could look at amplified oscillations, you could look at dampened oscillations, you could look at basically anything. Here are the constraints of the project. I want you to I'm going to actually ask you, unless you're a senior, to do the actual measurement. So this is going to be something where it's not just, well, here's what I would do. You're going to actually carry out an investigation over the course of the next several days in class. I want it to show simple harmonic motion. So whatever you do, it's got to be oscillating in such a way that the position, velocity, and acceleration versus time graphs are sine waves, right? Sine, like not sine functions, but sine waves. And you're actually gonna build this and take measurements, so it's gotta be something you can really actually work with. You can't say like, well, if we hooked the moon up to a big spring, what would happen? And it's not gonna cut it. And then I want you to have a question, a target in mind that you're gonna look for. So for example, what is the equation for the period of a 2-spring 1-mass system? Or like with pendulums, one of the things you can do is you could look at, well, we know pendulums are approximations of simple harmonic motion. This object is not moving side to side, it's just mostly moving side to side. But the more I increase the amplitude, the less side to side it is, and the less the motion is actually harmonic. So this is no longer exhibiting simple harmonic motion. You can see that with a motion sensor. You'd see that it's not exhibiting simple harmonic motion anymore. So if that's the case, then at what point does it really break down? I suggested like 20 degrees or so, but what do I know? Like, I just made that up. So you could ask those kinds of questions. You could ask a question like, how much force would a spring need to exert and at what frequency in order to keep a pendulum moving so that a clock keeps time or something like that. And then the next piece is, what are the actual measurements you're gonna need to take? And this is mostly so that I can think about equipment and supplies. Like if you say, well, I'm gonna need a force sensor, we got that. I'm gonna need to be able to measure motion with a motion sensor, got that too. And then if you're like, but I also need a Geiger counter to measure the radioactivity, I don't think I have a Geiger counter. I might, but I don't think I do. So that would be something, if I wanna know how you're gonna make your measurements, you may not be able to figure all that out today, but I want you to do the best you can. And then, one of the requirements is, I would like this to be more complicated somehow than what we did in class. In class, we used a pendulum, and we measured time, and we measured displacement. We used a vertical spring mass system, and we measured displacement and time and mass. What I would like you to do is increase for your project the complexity of either the system itself, the measurements that you make, or both. And I want you to tell me how your system is going to be more complex. Okay? So that's your job right now. I'm going to ask you all, if seniors, this is the last thing you're ever going to have to do for me, but the rest of you, this is just the start of what we're going to carry out for the next couple of weeks. I'm going to ask you to put this together in small groups over the rest of the class period, and then we're going to start working on this stuff on Friday.